Okay, any questions before we get started? Couple things. We'll have a math club on Friday, 5 o'clock in Mark and M102. Keisha Cookson will be talking about how to do. It's kind of a math poster thing. How to do a poster. How many of you in engineering ever have to do poster presentations for computer science? Sometimes you have to do these conferences, whatever. This might be kind of an interesting thing, and you know, at some point you'll probably have to do a presentation wherever you work. Also, remember, many of you have not done the assessment quiz, so please take advantage of that. You've got until Monday, the end of Monday's office hour, so make sure you do that if you haven't already. Okay, questions? All right. Yes. Yes, that's good. That's where you just come by and we have a little chit chat about where your progress is. You get a free extra 100 on your quiz. So, okay, so we're going to talk about the rank of the matrix a little bit. So here's kind of a warm up brain teaser. Suppose, just for the sake of argument, that you have, oh, by the way, before we start also, the last 2 quizzes that you all took, actually 3 quizzes ago, the average is really high, like an 80, which is really good. The last 2 quizzes have been a little bit lower, which doesn't concern me much since things curve, but just make sure that you know how to do it. So if you struggle with that, can't figure it out, you see me, I'll be happy to go over it. So suppose you have a 47 by 73 matrix, right? Now let's suppose I don't know, 29 linearly. You get this huge matrix, and you've got 29 linearly independent columns. So that means if you went through and you row reduced and you found the column space, you'd have 29 pivot columns that generate the column space, right? What are the possibilities for the number of linearly independent rows? Right? I mean, think about the rows, right? I mean, you can think of the rows as vectors as well. They're just written in the other order. What are the possibilities? Yeah.
29 independent rows.
So only one possibility, right? And that is exactly right. You all think this is obvious? Right? Is this immediate? I mean, obviously you answered pretty quickly, but can you explain why?
Well, because the way the columns work, they have to be like, it's kind of like Stokie. They can't like be on the same column or same row. So if they're not on the same row, then
Okay. Yeah. So we'll go through this actually. Let me point out, so let's start by looking at row space. Just like you have column spaces with the column vector, you can have a row space, row vectors, right? No difference. And in fact, the row space can be thought of row space, let's say of matrix A, can be thought of as the column space. What? Exactly, the transpose, right? Because when you take A and you transpose it, what do? You turn the rows into the columns, right? And so now you're just taking the rows and sticking them up on their end. Right? It's essentially the same thing. But that being said, I'm going to work with row spaces just like the rows for now. So let me start with the theorem here. If two matrices A and B are row equivalent, then the row spaces are the same. This is a little bit stronger than what we said in column spaces. And in fact, if B is an echelon form, the non-zero rows of B form a basis. For the row space of B and equivalently row space A. Now, this is actually a little different and actually a little better in a certain sense in the column space, right? Can somebody remind me, what is the process that you go through to find the basis of the column space? Yes.
You row reduce the matrix,
Right.
you find the pivot columns, and you take the same pivot columns from the original matrix and match it.
Right, you remember you had to go back, right? So you take a matrix and you row reduce it, right? And then you find the pivot columns, make the pivot columns with the first and the second and the fourth. Now you got to go back to the original matrix and jerk out the first, the second, and fourth columns, right? You don't have to do that with row spaces, right? Row spaces, what happens is you just reduce it, just like you would do in a column space, and pull out the non-zero rows. And those rows, the reduced rows, actually work. Because the row, because really when you're doing row operations, you're not changing anything there. So let's do an example here. Let's do the whole 9 yards. So suppose we have this matrix here. Let's go 4, minus 4. 12, 1, 3, 1, minus 1, 10, 1, 2, 12, minus 2, 6, and 4, minus 1, minus 6, 11, That's the set. Now, what we want to do here is I want the whole package. So I want to find let's throw the kitchen sink at this, do everything. I want to find a basis for row space. I want to find the basis for a basis for the column space, and I want to find the basis for the null space. Now, by the way, and basically the good news is all I got to do is row reduce all, right? So doing row reduction here will actually give me an echelon form that I can use for all this. First of all, let me kind of see where I'm at. The column space of A should be a subspace of R what? R4, right? Because the columns are four-dimensional vectors, right? Row space should be a subspace of R5. Very good. Null space, subspace of R4 also, right? So let's reduce this. By the way, does anybody see a group reduction that I can do? Makes sense. Yeah,
Take the 3 and multiply by negative.
what's that number?
Take the second column and multiply it by negative 1 back.
Second, oh yeah, I can do this. Yeah, but I'm you know what I want to do? I'm gonna use the third one to take this one and this one out first. And there's a reason for that. But actually you can do anything you want. I'm going to use the third row. To do some damage. I'm going to multiply by -2 and add it here. Times -2, -2, times -2. Convenient. I'm just going to -1 and add it here. So I'm taking a page from your book there, Cassie, and I'm going to turn this into a 1, right? I'm taking 1 and add it here. 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 1. And I'm going to multiply this by -2 and add it to the top. 0, 0, 0, and 0, -1. I am really digging in my top. Everybody okay? Yes. Now, just to kind of get my bearings here, I'm going to sort of rearrange this a little bit. 1, 1, 1, 4, 0, 2, 0, -2, 6, 1, 0, actually, I'll change the sign on that. 1, 2, 1, 0. And I'll put this on the bottom, changing the sign. Okay, I'm going to use the top row to take out this 2 here. I'll systematically go down now. Number 1, 1, 4, 0. That's 0. I'll take the 2 and add. Take 2 and add. Take 2 and add. 2 and add. And now look at that. All right. One, 0. I'm going to multiply this by 2 and add it here. Times 2 and add, 2 and add, 2 and add, that's 0, 0, 1, 2, 1, 0. These two are the same. So basically, I'm going to use this one to take everything in this column out. 1, 1, 1, 4, 0. 0. I'll put this one here. 1, 2, 1, 0. Take that out. And one more step, just because I'll let go over this section on form. 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 1, 0, and 1, 0, minus 1, 3. Now I've got this in row reduced echelon form, I can pretty much pick off what I want. Let's look at this theorem. This is my roll of matrix B, and the original one is A. This one is equivalent to my original matrix, because of row equivalent to the original matrix. So it says that the non-zero rows are a basis for the row space. So in this case, I write some row vectors, 1, 0, minus 1, 3, 0, 0, 1, 2, 1, 0, and 0, 0, 0, 0. Row spaces are cool because you can use your finished product, just the non-zero rows, period. Everybody open? Column A. That's basis. Now for the columns, we have to figure out what the pivots are and go backwards. Looks like rows 1, 2, and 5 are the pivot columns, right? Or, I'm sorry, columns. 1, 2, 5, 4. So we got to go back to the original one. Column 1 in the original matrix is 4, 3, 2, 4. Column 2 in the original matrix is 0, 1, 0, minus 1. And the fifth column in the original matrix is 1, 1, 1, 2. By the way, what is the dimension of the row space? It's 3, because space has 3 elements. This is a 3-dimensional subspace of R5, right? Which lives in R5, it's got 5 coordinates, but it's only got 3 basis elements. Right, okay with that? What's the dimension of the column space? Also 3. It's a 3-dimensional subspace of R4. It's got 3 basis elements. After we've done this computation, can somebody clarify why the row space and column space have the same dimension? How many vectors do we have in column space? 1 for each pivot, right? And the pivots also highlight the non-zero row, right? So they're exactly, if you have a row reduced echelon form, there are exactly as many non-zero rows, that is the number of basis elements of the row space, as there are pivot columns. Everybody agree with that? That's why the row space, column space, always the same size. Right, okay? Same size, meaning same dimension. Finally, we need to do null space. So let's do the null space here. Let's look at our row reduced echelon form here. How many free variables do I have? Right. Which ones are they? because columns 1, 2, and 5, they correspond to basic variables, 3 and 4 are free variables. So I get a couple of equations here. The first one across the top is x1 minus x3 plus 3x4, 0. And I get x2 plus 2x3 plus x4, 0. And I'm digging on the last equation because it's x5, 0. So your basic variables are all in terms of free variables. So here's what a typical element of the null space looks like. The null space is a subspace of R5. I think I said earlier it's a subspace of R4. I seem to remember that. That was a mistake. A subspace of R5. So use these equations here. X1 is x3 minus 3x4. X2 is minus 2x3 minus x4. X3 and x4 are free, and x5 is 0 by the last. And so this can be written as x3 comes to vector 1 minus 2, 1, 0, 0 plus x4 comes to vector minus 3 minus 1, 0, 1, 0. So my basis here is the vector 1 minus 2, 1, 0, 0 and minus 3 minus 1, 0, 1. Yes, sir.
So this would have a dimension of 2.
I'm sorry, what was that?
So the null space would have a dimension of 2.
That is correct. Can somebody give me a gut check for that? Right? Why does that make sense? Yes, Kathy. The dimension of the column space plus the dimension of the null space has to be the number of columns, which in this case is 5. You got the column space to have dimension 3, so this makes sense that this should be 2. But it's got to add 5, right? Because, and in fact, that's a theorem. And I'll write it down while fresh in our minds here. Here's the definition. And we've seen this before. Actually, this can be anything. It's actually. When you hear the word rank for a matrix, that is the dimension of the column space. And if you remember, the dimension of the column space is the number of linearly independent columns or the number of pivots. So here is famous rank nullity theorem. Yeah. A is an n by n matrix. Then dimension of row A equals dimension of column space A. Of course, the dimension of column space of A is defined to be the rank of A. This is the theorem part. The dimensions of column and row space are the same. And here's the rank nullity part. Rank of A plus the dimension of the null space of A is equal to the number of columns of the matrix. Okay. So let me kind of just outline what we kind of thought our way through this. The dimension of row A equals the number of non-zero. So that's what we had earlier, that what you do to find the row space, is you reduce the matrix and the non-zero rows that you end up with form the basis. This number, that is the number of non-zero rows, is equal to the number of pivots. Right? Which is equal to dimension of column space. So the number of non-zero rows is exactly the same thing as the number of pivots. And the number of pivots is equal, of course, to the number of pivot columns, which is the dimension of the column. So that establishes these two are the same. And notice that for the rank nullity part, we point out that the rank of A, number of pivot columns rank base just the number of pivot columns. The dim of the null A equals number of free variables. Right? Which is exactly equal to number of non-pivot columns. Because after all, how do we find which are the free variables? They're exactly the ones that correspond to the non-pivot column. Now, I don't know much, but I do know that if you add the number of pivot columns to the number of non-pivot columns, what do you get? The total number of columns. So, rank of A plus dim null A. Number of pivot columns, number of non-pivot columns, equal to the number of columns. Any questions so far? Okay. Yes, sir.
So, what was the dimension of a single vector?
Uh, well, we need to restate that a little bit. The dimension of a vector doesn't make sense. You only talk about the dimension of a space. But, so you're asking, so let me write something down and see if I'm interpreting the question. Right? Is that kind of the question you're asking? Well, what if your matrix is just a vector? Well, it's no different, really. I know it looks a little strange because there's only one column, but you can do the same thing, right? Row reduce A. Okay, so far? Okay, so row space. Is generated by the row vector 1. The row space is one dimension, right? Because the rows, they're only one line, right? How many pivot columns do I have? 1. You're gonna go back to the original, the column A basis. Is that. And how many free variables are there? 0. 0. It's the only basic variable. You get x1 equals 0. Right? I mean, that's essentially the equation. So the null space, well, here, this is what a free value. Right, so that's your null space because it's 0. This is vector. This row, this column, this row, this column. So you can still do all of this, right? It's just only with only one row. Oh, I'm sorry, in this case, you're only one column. Any questions on it? Yes.
Just
What's that?
null space, just technically not.
No, the null, there's always something in the null space because there's always 0. And in fact, in this case, it's always 0. Right? So think about it this way. I mean, this is actually easy to see from another point of view without doing all the, I actually looked at it in terms of equations, but take something in the null space. 1, 1, 2. Now, of course, this is a 3 by 1 vector, and so multiplied, it's got to be a 1 by 1. So what is this here? This is multiply this is x, x2, 2x, so multiply this has 0, 0, 0. So all these equations mean x equals 0. So the null space is only 0. Okay. Others, yes.
The dimension of the null space would be 0.
Yes. If you have the 0 vector as all there is in space, then the dimension is 0. Because there is no linearly independent vector in the 0 space. Right, and we should see that all working out here because the dimension of the column space is 1. The dimension of the null space is 0. And 0 plus 1 is the number of columns. You might try to lay this matrix on the side and do the row matrix 1, 1, 2, and see what you get there. Okay, I'm going to go back to invertible matrices again and tack on some other stuff because of what we've learned here. We'll do another example. Okay. Noticing this theorem again, I am assuming that the matrix is square. It is actually n by n. And there's a reason for this. First condition is A is invertible. So this is back to this invertible matrix stuff. 2, the columns of A form a basis for Rn. Number 3, the column space of A is all of Rn. Number 4, the dimension of the column space of N. The rank of A is N. And finally, the null space of A consists of only the 0 vector. Finally, M dimension the null space of A. So, if A is invertible, you can row reduce it to the identity matrix, which means the columns of A are all linearly independent and therefore form the basis for Rn. Because there's n columns, n linearly independent columns, and Rn automatically have to be a basis. And of course, the columns form a basis for Rn, and the columns are all of Rn. Which means that the dimension of the column space is n, all of Rn. This is silly because rank is defined to be the dimension of the column space. There's nothing there. The null space of A is 0. Why is that the case? Because that means if you can row reduce this, if you can row reduce A to the identity matrix, there are every column within the column there are no free variables. Means the null space of A is 0, which in turn is the dimension of the null space. Okay. Any questions? Good luck. All right, so one more problem. I pulled this one off an old, this is one that I actually gave before in, like previous class, but I thought it was kind of worth looking at. Suppose suppose that this is a linear transformation. And P of X. Okay, so suppose I have a linear transformation from R30 to R20. And I'm going to represent this linear transformation as a matrix. So T of X is A times A. Right. Okay, first thing. Okay, let's just make sure we're on. Let me start. It's blank. Wow. What's the size of the matrix? Yes.
20 by 30.
20 by 30. How can I kill this? The clue is this. Your input is a vector from R30, right? So that is a 30 by 1 vector, right? This multiplication has to make sense. When you multiply 20 by 30, comes a 30 by 1, you get a 20 by 1, which is exactly what we need, right? Everybody okay? See how we dug that information out? Number 2. What is the maximum possible value next to the null space today? Yes. Okay, what did you get?
So there's, oh wait, yeah, there's 30,
Okay, there's 30
20
columns.
rows. And that's what that means. Oh. Okay, one second. So you have 20 columns, you have 30 columns.
Right. 20
And
rows, 30 columns.
you would have a maximum of. So the maximum of.
Let me ask you this. What's the matrix that you might think of that makes the biggest null space of all?
Just.
Is it? You're on the right track. And sort of the other extreme. The 0 matrix, right? That kills everything in sight, right? That's like Wile E. Coyote blown to pieces, right? Now, if you have the 0 matrix, you've got the 0 matrix. How many free variables? You're thinking, so how many pivot columns do you have in the 0 matrix? You've got 0 pivot columns, right? So that means how many free variables do you have? Right, 30, right? One for each. Remember, another way to do this, so I did the example of the 0 matrix, but think of it this way, right? The dimension of the null space plus the dimension of the column space should be 30, right? So let me kind of scribble that down. Everybody agree with that? That's our rank nullity term, the dimensional conflict, dimensional null space. Third. How do I make this as big as possible? By making this as small as possible. And I can certainly make it zero, right? Because I can fill all the columns to zero, forcing that to be third. That's another. Everybody agree with that? What's that? Yes.
This one should be 10, like the lower one should be 10. Because you can only have like a maximum of 20 pivot columns.
That's correct. The dimension, how do you make the dimension small as possible while making this as big as possible? Right? Everybody agree with that? So what is the maximum amount of pivot columns you can have in a 20 by 30 matrix? Right, because you're limited by the 20 rows. Everybody agree with that? So the biggest this animal can be is 20, making that. Everybody follow this? Okay, how about this one? How about what is the maximum dimension of the null phase transpose? Now recall a transpose is 30 by 20. Yes. Would you say it's correct? Again, it can be zero matrix. So you could have all 20 columns in this being zero. What is meant? Then null. Correct. It's zero. So here's the last one. How about this? Suppose M of the column face A is 13. What is M of the null of A2? Anybody know this one?
17.
What's that?
17.
17?
Yeah.
I think it's 7. Yeah, let's check that. So let me write this down.
Oh, sure.
Notice I've replaced my formula just A with AT. The dimension of the columns of AT plus the dimension of the null space of AT should be the number of columns in AT. How many columns in AT? 20. This is what we don't know. Can somebody tell me what the dimension of the column in AT is? this is equal to the dimension of row A, which is dimension of the column space. Right? Which is what, 13? So what I get is 13 plus m null AP is equal to 20. So the dimension null AP is 7. Okay, any questions on that? Okay, well, you all have a good one, and we will see you on Friday.